want to talk about today is Google. And, if I was in a classroom and I could see your faces, I would say, well, what do you think when you hear the word Google? If you want to type something on the chat, I'm looking at it. I'm just curious, what is it that Google means to you these days? Anybody? Giant conglomerate of things. Cool. Anybody else? Readily available information. That's a really good one. Yeah. How you get to places. Jose, you don't use your phone for that. I guess you.
I mean, Google Maps.
Google Maps for that. Well, yes, Google is many things these days. If you were old enough as I am, then you would remember a time where Google was not such a big thing. I would say that when I think about Google, I think of it as a big company. It's really a big company these days that controls a lot of the information that is out there on the internet. Google itself does not own the internet or the web for that matter, but it operates one of the most popular by far search engines that exist in the world. I would argue that these days it's pretty much a monopoly when it comes to search engines. And how we got here, it's a little bit of an interesting story if you're too young to have seen any of this. So today we're going to be talking a little bit about what Google did and about search engines in particular, because that's how Google started. Google started with just the search engine. And the idea of a search engine was we wanted to have a program that would allow us to navigate the web. And that's the big sort of network of web pages that we are very familiar with today. And in particular, Google, the search engine, what it would allow us to do is to find specific web pages. So we're looking for a keyword, and we're trying to find all the web pages or many web pages that might have relevant information about that keyword. That's where the search engine comes in. And I think of Google these days, it's a lot more than just that. As Jose was saying, it operates, it creates and maintains and operates one of the largest maps of the world, which is what it uses to feed into the programs that allow you to find the best routes to go and drive from one place to another. It also manages an amazing amount of information in how each of us is being shown specific advertisements. So Google knows a lot about us so that they can sell our profiles to the advertisers so that advertisers can know which are the ads that when we're browsing the internet would be good for us to see or will make us likely to want to buy something from there. So in reality, it's pretty much in every aspect of our lives these days, but it wasn't always like that. And before I get you a little bit to that sort of old past of the internet, let me recap a bit and remind you, when I talk about the internet, what is it that I mean and how that is going to be different from what we normally refer to as the web. The internet itself, it's a big network of computers or servers all around the world, and they're connected through wires. And I put wires in quotes because many of these connections would say, well, I'm just have Wi-Fi from my computer to the modem in my house or in my office or in my school, which is true. So some of these wires, they're still physical, they're just wireless, but they're there. And these are, let's say, undirected connections, right? There's two computers, there's either a physical wire that puts them together, or there's a Wi-Fi connection that allows us to do so through the air. But either way, the connections are referring to from one computer to a modem, from a modem to a server, from a server to another modem, and so forth. And these connections and the computers, servers, modems, etc., they define a graph, a very, very large graph that consists of servers and computers that are our vertices, and the connections, as I said, wired or wireless connections that connect these computers, modems, servers, etc. This is an undirected graph, and I really like this picture of the internet many years ago when it was still fairly small. And what's nice about this picture is it's an artistic representation. As you can see, or you probably have figured out by now, is that for any given graph, there's a billion ways of representing it, right? I could take two nodes inside here and put them on opposite sides, but this representation puts them together so that they look like a cluster. And some of these really bright points represent nodes in the internet, let's say big giant servers that have way too many connections. So because they have so many connections, they look bright in the picture. So it makes it look really pretty. This is part of an art collection in the MoMA. So if you're ever interested, there's an art to visualizing graphs. And this is a very pretty one of the internet. So now that we have the internet, which is the physical network that connects the servers and computers, we can also think of the virtual network that is the World Wide Web. The World Wide Web doesn't actually exist physically, right? It's just a bunch of web pages that exist in the virtual space. And those web pages are connected by links, right? And the links are usually directed. So if I visit a website, I will see many hyperlinks that will take me to other websites. Sometimes the hyperlinks take me back to the same page or different parts of the same page, but most of the times they actually take me to a different website altogether. So what these links represent from the graph point of view, these are the edges, and they're usually directed edges because from one page, it takes me to another one in that direction. And it doesn't mean that that page will have a link to get me back to where I started. And the web pages correspond to the vertices. Now, in terms of a little bit of the history of the World Wide Web, well, it was born in 1991, or that's the agreement, when the first browser was created. And the first browser, if you wonder what the word browser is, you can think of the Internet Explorer or your Safari. This is a program that allows you to be able to read many different files of different types from many different computers. So the browser part is just the interface that allows you to open, HTML code, but it also allows you to see to get the PDFs. It allows you to see, videos. It allows you to listen to music. So those files come in different flavors and different formats. And the browser is that interface that allows us to access it, to be able to see what's in there and see the content without necessarily seeing everything that was behind. Those of you, if anybody is old enough to remember, there was a time where in order to download pages in files from somebody else's computer, you had to do something called an FTP connection. Yeah, that's all time since that happened, but yeah, it's still there. So once that first browser was created, you can imagine that was just the program that allowed people to go to, hey, I'm going to go and look at Jose's computer and I'm going to download from his computer these files that I want. And then maybe some other student would come and say, oh, I'm going to, log into Mariana's computer and I'm going to download some files from there. So that was the browsing part, but it's still not the part of finding what is there, right? So what is there for me to find in Jose's computer? What is there for me to find in somebody else's computer? That part is what had to be created later, and what we're gonna call the search part of the internet. So back to the history of the internet, the first free web browser that there was called Mosaic. And once there was a free option for people to go and look at other people's files, then, the web just started growing exponentially fast. And as you know, it keeps on growing. It doesn't stop. And it's constantly changing and constantly evolving. After Mosaic came around, then you might have heard of some of these. Many other browsers appeared. The Internet Explorer, still out there. Netscape Navigator, I don't even know if I haven't seen anybody using one of those lately. There's a Mozilla, Firefox, Safari, Google Chrome. you have many options when it comes to browsing, depending on which one you like. Each person might have their favorites. Some of these probably are not even around anymore. And who knows, maybe some new ones will come in the future. So that's one component, which is the browsing part. But now we are browsing through tons and tons and tons of data. So how are you going to go and say, well, fine, I can see what's in Jose's computer, but if there's too much of it, I'm going to get lost. So instead of just browsing, I also need to find the information, right? I need to know what is it that I want to browse. And I want to do that fast, so quickly and efficiently, because I'm going to be doing this a lot, and we're going to have millions of users doing it at the same time. So this was sort of the need to come up with a better way of organizing and finding information. And that's where the search engines came around. So again, from the very beginning, it was apparent that we would need programs that could allow us to find information, to search through large databases out there, computers of millions of different people around the world. But we wanted to find specific pieces of content that we might be interested in looking at. So that's where the search engines sort of began, right? The idea is not just to be able to access the files once we're there, but how to find them to begin with. So these are two different parts, even though in most cases they come in the same program. You have your Internet Explorer, and that has a search engine that it's working on by default. You can sometimes pick which one you want to use, but these days, as most of our searches are being done by Google, unless you really insist of doing something different. So the search part is the one that I want to focus on today. Right. And at the beginning of the internet, back in the early 90s, there were actually a lot of search engines. And again, maybe most of you you're too young to remember, but there was a time where we would never have thought of using the word to Google as a verb. That came later. I remember personally, I think I remember using Excite for many of my searches. I remember using at some point Alta Vista as well. And each person, a friend would tell you, hey, you should try this, you should try that. I like this one better. It looks nicer. This one seems to be faster. And I remember back in college, some of my last couple of years in college, where one of my professors told me, hey, why don't you Google this? I'm like, what? Google what? And they're like, yeah, this is a really nice search engine. You should try it. It's very fast and it gives better results. You would wonder, like, what does it mean to get better results? And I'll pose that question to you. Why do you think it's a good result in a search? What are you looking for when you're searching for information on the web? Anybody? To be precise. So you want to get exactly the keywords that are their velocity. So you want, that you want your search to be fast. You want it to match what you want to know, right? You want it to be accurate or relevant. That's a really good one. Relevance. So I could go and do a search right now for maybe UNC, right? Which is my home institution, University of North Carolina. And I might be interested on looking for something specific to the next basketball game. But, there's a lot of websites out there that are going to have UNC on them. And maybe some of them are not going to be relevant to what I'm looking for. And maybe, who knows, for some other keywords, my keyword search might return a lot of web pages that do have the keyword, but they're irrelevant, right? That they don't have anything interesting in them other than having the keyword there. So it's not enough to just do a search for tree and find a website that has the meaning of the word tree versus another website that might have a website about a forest where certain trees are grown, or another website that gives me some interesting types of trees or something else. So you can come up with a million examples where the key is that we're looking for relevance. And that became very quickly at the beginning a hard thing to do. So if you think about the most naive way of creating a search engine, you would think, well, all I need to do is you give me a keyword, let's say tree, and I'm gonna go and look through all the files that I have access to. I'm gonna find all of the websites that have the word key in them. So I'll come back, and I'll return to you all those. You can imagine that if you wanted to do that right now, you could spend probably your entire life going through the results to the keyword search tree, if it was just a matter of finding all the files that have the word tree in it. So as the web grew bigger, and now we're talking about billions of web pages out there, just a simple search would return just an absurd number of results. And that's not useful. That's not relevant. That's not precise. That's not accurate. That really is not helpful, right? So that means that somebody had to come up with an idea of deciding, of all the websites in the world that have the word tree in it, which ones are the better ones? Which ones are the more relevant ones? And the great idea that the Google creators had was to try to rank all the websites on the internet, give them one number that would be some kind of measure of its relevance, right, for each website. Now think about it. You can't really go and evaluate the content of each website, and the content of one website could be really relevant for one purpose, but maybe not so relevant for other purposes. So you have to come up with some kind of ranking that does not actually need you to look at what the content of the website is. So this was sort of the task back in 1991. And the creators of Google, whose names were Page and Brin, came up with a really good idea. They came up with the idea that if you could give a universal ranking that was somehow meaningful of the value or the relevance of a website, then you could use that number on any given search. So I'll do my keyword search for the word tree. I'll get, 1 million results that have the word tree in it. But now I'm going to show them to you in the order of their rank. So the ones that have been deemed really relevant for whatever reason are going to show up at the top. And the ones that have proven to be irrelevant will show up at the end, which means you'll probably never get to them. On average, most of us will probably just look at 1, 2 at most pages of results. So how many can you fit in there? Like 10, 15 sites at a time. So you can see that we lose patience very quickly. So this number of relevance, or these ranking that we're going to give the web pages, is actually very, very important in controlling what you get to see when you do a keyword search. So this idea actually worked great. And they figure out a way that actually tells you quite well, it's not perfect, like nothing is, but it's quite good at finding relevant content. And that set Google aside. So before I go and explain how the original algorithm that Google was founded upon works, let me do a little bit of a recap of some of the things that we have talked about in the last couple of weeks. So remember, a graph is going to be a set of vertices and a set of edges that connect them, right? And the graphs can be directed or undirected. So in the context of today, I'm going to be mostly interested in the web graph, which is going to be a directed graph. Now, the specific structure of the graph does matter quite a bit, and in the sense that, as we saw in some of last week's simulations, depending on how my graph looks, certain properties do change. Some of the properties that change from one graph to another has to do with the number, whether the graph is connected or not, whether for any given pair of vertices, can I find a path that connects them? If it's a directed graph, can I always find a path that goes from one specific vertex to another? Or maybe there's a subset of vertices that have paths in both directions. Remember what we call a strongly connected component. Another question that we might be interested in is in understanding what is the typical distance between vertices. Again, if you think about large graphs with billions of nodes, well, it's important that it doesn't take you billions of steps to get from one part of the internet to the other, right? That's crucial. So what we want to make sure is that even though that the scale of the graph is humongous, it doesn't take us very long to go from one server in particular to another, or from one web page to another. We're also interested on the properties of the number of neighbors, so the degree of a graph. In a directed graph, we usually care about the inbound number of neighbors and the outbound number of neighbors separately. And as it turns out to be, for the analysis of the algorithms we're going to be talking about today, this particular quantity does play a very important role. So some of these things matter, and to the extent that they matter when we're looking at a graph, we want to make sure that we think of the web graph or of the internet as graphs that we know enough about, that we can say whether they're connected, whether they're not connected, whether distances are short, whether distances are large. And remember, not all graphs have the same structure, and we went through several different models that have different properties. And you can imagine in the real world, not probably any real world graph is not specifically or exactly one of those models, but they will share some properties with one or several of those models. Now, on the other hand, when we talk about the internet, we're talking about a very, very large graph. And fortunately for us, the fact that it's so large makes it rather special, because we can say a lot of things about what matters for analyzing things that happen on it. So specifically analyzing how these ranking algorithms are going to work. And that's an important feature that we like to have. For the purpose of ranking methods, usually I like to think of the web graph as, let's say, maybe an inhomogeneous random graph where, like the one that we looked at in lecture to the Chung Lu model, for example. That would be a good way of thinking. That model captures the features that are most important for studying, for example, rankings. So now that we remember a little bit of what we saw about graphs, the examples from today on the internet, we're talking about millions or billions of vertices. These are really, really, really large graphs. However, even though there's billions of web pages out there, it turns out that the ratio of edges to vertices, or the average degree of the graph, is not in general big. Even in social networks like Facebook, the number of users is in the millions, but the average number of friends that somebody has is around the 200, 300 level. The average number of web pages of links that a website will have is about 30. So despite the fact that the graphs are humongous, the number of edges to vertices is it's not that big relative to the size of the graph. And what this makes them, it makes them very sparse. That's why we usually refer to graphs like this. On top of that, some of the properties that we've seen during this course are also satisfied by both the internet and the web graph. The first one is a small world property, which is that the distances between vertices and the World Wide Web or on the internet is actually very small. Again, if you're comparing to billions, on average, a small distance could be something like 6, 7, 8. That's a very small distance that has nothing to do with the size of the billions that the graph itself, the number of vertices the graph itself has. So definitely the small world property tends to occur in these large graphs. And the other one is the scale-free property, which says that the proportion of vertices with, let's say, k neighbors decays as a power law, which means it doesn't decay very fast. And let me take a little break to go back to that picture of the internet here. These guys, the very bright stars, are very high degree nodes. And you can see there's many of them. So overall, this is a very inhomogeneous graph where just some of these vertices are abnormally big Whereas the great majority of them, you can't even see them. Here's, you can see a few, they're all sort of small. They're not special in any ways. Here, there's nobody that is particularly big. However, these ones, in terms of the number of them, the number of them is not that small. And that has to do with a scale-free property. That's basically these, because although the average number of neighbors in Facebook is not that great, there are some people that have probably 1 million friends. So, you can see that there's people who have hundreds of thousands of friends, and they're not that few of them. Think about celebrities in general. They will have way more friends than your average person, which still has, a small number of friends. So some of the other things that matter for the study of the web graph is that the web graph in particular is a disconnected graph, right? So you would think like, well, nothing that what we do is going to work because it's a disconnected graph, but that's not entirely true. Even though it's a disconnected graph, it has a very large subset of vertices that are connected. That's something we call a giant strongly connected component. So within that group, and what it makes it giant is the fact that it has a positive proportion or positive fraction of the vertices on the entire graph. And all of those will have paths going from one place to the other and a potentially different path from here to the origin again. So when we study things like this, the fact that it's disconnected doesn't matter as much as long as we have these sort of giant strongly connected component. Other properties that we discussed during this course, but that I'm not going to be talking about today, are those clusters or communities. Some graphs will have lots of, heavily connected clusters or communities that separate themselves. That's important, and there are things that are related to ranking as well when we talk about communities, but I won't cover those today. And another thing that matters a lot for the study of ranking algorithms in particular has to do with the fact that on the internet, if a website has a very large number of in degrees, it also has a good chance of having a very large number of out degrees. Now, if you think about the web graph, the in degree are the connections that other people decide to put towards a specific website. So these are external validation, let's say. Whereas the out degree is who you choose to connect to, which is also a sign of your endorsement towards another page. So if you're creating your own personal website, then you have direct control of where you draw links towards, right? So you have control over the out degree because you decide what other pages you want to endorse. However, you don't have direct control of who's going to have web pointers towards your page. And that's sort of the key idea behind many of these ranking schemes that we're going to be talking about. Okay. Now, if we think about these properties that graphs can have, well, you can think, well, what else do those properties influence? Well, if you think about propagating ideas, propagating messages, propagating, epidemics of any kind, physical or not physical, well, when those connections are there or where those connections are weaker, that determines a lot who can get that message, right? Like, so let's say that I want to send the message and put it on a very important website, and with the idea that many other websites are going to create links to that website because it's very important, it's very central, and then other people will eventually create links to those. So a lot of traffic, virtual traffic, will end up coming to visit my website and will eventually get to see the message, right? So that's something that matters quite a bit when we're thinking about how the information is moving across the web graph. And it is important to be able to know which are the vertices, which are the websites that are central, that have the power of spreading information more efficiently. How many other websites it can reach, how many people are going to come and visit and see what's inside that website. So that brings us to the topic of network centrality. So network centrality is a measure on a graph that tells us how central specific vertices are. And their centrality is related to propagating messages or to receiving a lot of traffic from users. All of these properties are closely related with the small world phenomenon, with the scale-free property, and with some of these other properties that I mentioned here. So you can see everything sort of connects when we're thinking about the internet. So now let's go back to what is it that centrality and relevance and how they are related when we're talking about search engines. So we want to talk about centrality and relevance as two separate things. Relevance is something that has to do with the content of the website, right? It's the information inside. Centrality, on the other hand, is something, it's a graph property. It's something that doesn't have to do with the content, but that has to do only with the edges or how well connected a vertex is from the graph point of view. So how are these two ideas put together? Well, the key idea behind Google's algorithm, which is called PageRank, is that nodes that are central from the graph sort of theoretical point of view, are going to be vertices or websites that receive a lot of traffic or through which a lot of traffic goes through, right? So a lot of visitors, a lot of people will come and end up in that page and then go to other places and then keep coming back. So those central nodes are key to determining which ones are the relevant content, because if people keep coming back, right, then it should be that they're coming back for something. So if I find from the graph point of view a website, a vertex that is central to the graph, then somebody must have made it to be central, because it's going to be a vertex that gets visited a lot. And you could only make it be visited a lot if it has relevant content. Hopefully that makes sense. So the idea behind this algorithm is that relevance, which is something about the content, and centrality, which is something about the graph, are closely related. And the reason why they're related is because of the fact that it's people who choose where to put the edges to point to, right? We create websites, we decide where to go. On our own personal website, we might decide like, hey, you should check this out because it's fun. Hey, you may check this other website out because it has interesting or important information. And I go to a university website and I see a lot of information about COVID. And it has a lot of links of places, some of them sponsored by the government, that has a lot of information about COVID and what the country is doing, what are the health department decisions being made, whether what vaccines are being approved, which boosters are being approved, and all of those things. So obviously it's people who are making the decision to create those links because the content in the sites where that information is important or relevant. So essentially what we've come up with is the idea that if I can find central nodes, then I will probably be able to find relevant web pages, right? So the question is now something about the graph alone. It has nothing to do with the content anymore. So for me to explain how Google's PageRank algorithm finds central nodes, let me bring in some definitions. So we're going to use N to denote the number of vertices in the World Wide Web. Remember, this is a directed graph where all the vertices are websites and all the links are directed edges. To each website or each web page, we're going to give it a rank. Remember that universal rank that is going to be a number between 0 and 1. The closer to 1, the more relevant my website is. The closer to 0, the more irrelevant it becomes. So numbers that have page ranks closer to 1 are going to be the ones that we're going to call central to the network. So this is universal, which means on any given search, it's the same number. It has nothing to do whether my keyword search was just the word tree or my keyword search was, random graphs and trees. The content, the two searches are going to return very different kinds of results. However, the rank that is being used to choose in which order relative to that search my websites are showing is going to be determined by this number that doesn't change regardless of the context. An important observation that we can make is that relevance is contagious. And again, go back to thinking about how is it that we decide to create websites. So let's suppose that I already have a very, very important website that a lot of people come and visit. So I have the CDC's website on the latest information on COVID, right? So now I have a website that I know that already has gained a lot of attraction and that has been deemed respectable by a lot of people. And therefore it is a source that a lot of searches will lead to eventually. However, now that I'm so important, if the CDC decides to create a link to an external site, it's giving it its endorsement. It's saying like, hey, if you're interested in finding resources for communities struggling because of COVID, you should go and check out this other agency or organization that is helping. By doing so, it's endorsing it. And because the CDC's website is so important already, it's going to have a very high page rank. It's going to pass some of that relevance to whoever it chooses to endorse, especially if it's only picking carefully who to endorse. So by that mechanism, somebody who a website that is being pointed at by a very high ranked page is also going to receive a high page rank too. On the other hand, if the website, the CDC chooses to create connections to everybody indiscriminately, right? And just starts putting links without really thinking much about it to, hundreds or thousands of pages, then, it doesn't say anything, right? It just says, okay, you're just spamming everybody. And even though you yourself are a very important website, the fact that you have so many links out doesn't mean anything. Everybody can get a link, right? So in that sense, although it is contagious, it also discriminates to the degree that it only works, this sort of contagious mechanism only works if you have a few people that you want to endorse. So now let's talk a little bit about the mathematics behind PageRank. So at its basic, PageRank is nothing but a vector that happens to be the solution to a very large system of linear equations. That's it. There's no magic to it in any way. And what it says is the following. The rank of page I is going to be a weighted sum, weighted by these alpha and 1 minus alpha factor, of the weighted ranks of its inbound neighbors. These are the ranks of the inbound neighbors. Here are all the J's connecting to I of page I. And it's weighted by a factor of 1 over the out degree. So if I'm a very important page, as I said, but I have a very, very large out degree, then I'm not passing on much of my importance to the other pages. I'm just giving them a tiny fraction, which is proportional or inversely proportional to my out degree. So this defines a system of equation that happens to have a unique solution no matter what. It's always well defined. This alpha is going to be a number between 0 and 1 and what's called the damping factor. If alpha is equal to 1, the system of equations may not have a unique solution. But if alpha is strictly between 0 and 1, it does. And the sort of typical value for PageRank that most people use is 0.85, which is sort of a sweet spot between putting too much attention to my own neighbors and putting too little attention to my own neighbors and spreading the attention to the entire graph. So these damping factor is important, and this is sort of the traditional value that people give it. At this point, you would think like, well, if this is just a system of equations, why does it work? And does anybody have any ideas, any clues of why this would work at all? No? Well, here I'm going to be talking a little about probability because that's what we're going to need to make sense out of this. So let's suppose for a second that our graph is fully connected so that I don't have any issues. There are no disconnected edges, so it's all strongly connected. And imagine that I wanted to navigate the graph at random. So at random means by flipping coins or tossing dice or making some choice that has nothing to do with the content of the websites or anything. So I just sit in front of my computer, go to a website, find the links that that website has. Let's say that it has 17 links. And I'm going to just choose one of those 17 links with equal probability, with probability 1/17. And once I choose it, I go there. And the next step, I browse through the content of that, look at the links, choose one. This time there's 8 links. So I pick with probability 1/8, any of those, and go there. And I keep navigating the web by choosing at each step with equal probability any of the links that I have there. This is something we call a random surfer. And these random surfer, mathematically, what it's defining is something we call a random walk on the graph, in this case, the web graph, right? So it defines a stochastic, a probabilistic process that tells me at each step where I'm going to be standing. And it gives me a probabilistic rule to decide where to go next, given my current position. And assuming that my graph is connected, I can keep doing this forever and ever and ever and ever. If a node in this graph is central, what's going to happen is that as I go around in the random graph visiting points, I will tend to stop more often through the central nodes. I will come and visit more because there's going to be more paths that lead me there. And there's more paths, I'm going to be more likely to choose a path that gets me to those points. So by following this random walk, what I'm looking at is the vertices that I tend to stop for longer periods of time, or that not longer periods, because let's say that I spend 1 unit of time in each one, but the number of visits in the long run that I spend on each one, that's going to it's going to help me identify the nodes that are central. So here's a little picture to give you an idea. I have my random surfer right here. And this is a tiny little graph. It's directed. And let's say that I'm here at vertex number 1. I have 2 links that I can follow, one to website 2 and one to the website 9. So I toss a coin with probability 1/2 each, and I choose to go in one direction. So now I'm in 2. And from 2, I can go to 3, or I can go to 6. So again, I toss a coin and I choose to pick 1. So this time I pick 6. From 6, I have 1 to 10 and another 1 to 2 and 1 to 3. So I pick with probability 1/3 1, and I keep going. So now I'm at 3. Now maybe the next one I'm at 5. Then from 5, I can go to 4. I can go to 9. But let's say I go back to 9. Then maybe I come back. And then eventually I'm going to come back to 2. And then who knows, I'll keep visiting. Maybe at some point I can go to, if I go to 10, I get stuck because there's no outbound links. So that can happen. But if I go from 6 to 2, from 2, I can go to 3, from 3 to 5, from 5 to 9, 9 to 7. I can create a cycle right there, and I can keep coming back and so forth. So if my graph was strongly connected, then I could keep doing this, and I would go and visit certain nodes more than others because there's going to be more paths that go through those nodes. Now, the problem in reality is going to be that the web graph is like this. It's not strongly connected. But before we get to that, let me show you how the interpretation works to define in mathematical terms what we're doing. What we define with these random walk is a Markov chain. That's the mathematical name that we give it. It's going to be a stochastic process that I'm going to call xk, indexed by the time step k. And this stochastic process is using randomness to decide whenever I'm in one step, where to go next. So what I'm keeping track of with these random variable is the number of the vertex that I'm visiting at time k. So I started with vertex 2, then I went to vertex 5, so x2 would be 5, then I went to vertex 7, so x3 would be 7, and so forth, right? This is something we call, as I said, a Markov chain, which is one of the sort of simplest stochastic processes that we have in probability. And Markov chains have a lot of interesting properties. One of them is the existence of something we call the stationary distribution. So specifically in the context of what we're doing here, if I were to count the number of visits to any particular vertex, let's say vertex I in the first k steps, and I divide that by k, and now I take the limit as the number of steps goes to infinity, this is going to be giving me the proportion of visits to vertex I. This is going to converge to some probability pi I. This is going to be a probability, it's a number between 0 and 1. This probability has a really nice interpretation. It has the interpretation of being the long run proportion of time that we spend in vertex I. So the number of visits in the long run relative to the number of steps that we take. And because this is the stationary distribution and it has that interpretation, it means that the nodes that are going to have higher values of this stationary probability are going to be the ones that have more centrality, because they're the ones that I keep coming back to again and again and again. As it turns out, that's exactly what the PageRank is when our damping factor is 0. So if we do not have a damping factor, then, or our damping factor is 0, then the PageRank vector is exactly the stationary distribution of this particular random walk. So the problem, as I showed you with my little picture, is that this doesn't work if the graph is disconnected or if it's not strongly connected, right? Because what's going to happen is what happened to me here, which is I get to node 10 and I can't go anywhere because there are no outbound links, right? So I got stuck. So once I get to 10, I'm going to spend the rest of my life in 10. So what is it that we can do in order to get us unstuck? I have one question about the getting stuck part, and that says, is there an average length for the walk of the random surfer given that the walk can get stuck? Yes, you can compute the moment until absorption. That's one of the questions. But rather than trying to get stuck, we're going to try to get unstuck. How can you get unstuck? Using some little bit of randomness. Anybody? Any ideas?
You can start again at another vertex at random.
I can start again at another vertex at random, right? If I get stuck, I can say, okay, let's start again and begin somewhere else. Well, that's actually exactly what we're going to do. We're going to tweak it a bit in order for this to work all the time in this context of our Markov chain. But what we're going to do is we're going to use a little extra coin flip to decide how we're going to get unstuck. So, sorry. What we're going to do is imagine that our surfer, our virtual surfer, has a coin with her. This coin is going to land heads with probability alpha, and it's going to land tails with probability 1 minus alpha, right? So instead of just choosing when we get stuck, we're going to choose in every step. So on each step, before we decide where to go, we're going to toss the coin. If it lands heads, I'm going to choose one of the outbound links of the page that I'm sitting at, if there is one. And if not, I'm going to choose with equal probability somebody anywhere else in the entire graph. If it lands tails, we're going to always pick from everywhere in the graph. So this basically fixes the problem in the way that you were suggesting, which is whenever you get stuck, you always pick with a uniform probability among all the websites in the World Wide Web. In this way, we can never get stuck, and we define a new Markov chain, which is a sort of adjusted Markov chain. And this Markov chain also has a stationary probability, and that stationary probability is exactly the PageRank. So now we can see that the PageRank actually has a lot of reason why it works, because it corresponds to the long-run proportion of time that the simplest of the random walks that we can define is going to spend in each particular state or each particular vertex. And we're going to tend to spend more time in vertices that have lots of paths that get there, right? And if a vertex has a lot of paths that can get me there, it means that people have created those paths. And in the creation of those paths, they're basically endorsing the content. Hence, centrality leads to relevance. Before we continue, let me talk a little bit about a few other network centrality measures that we have. PageRank is one of the most popular ones, and there's many reasons for it. One of them being that it's very easy to compute, and it can be computed even in a local way without having to know the entire adjacency matrix. But that's not the only one. Another sort of measure of degree centrality is the degree centrality, which is just saying if you're a vertex that has a very high number of neighbors, you must be important. And therefore you get a centrality score that is high. So one measure is just to look at the degree of vertices and say somebody is more relevant, the higher its degree is. Another measure is something called closeness centrality, which is saying, well, I'm going to stand in vertex I, and I'm going to look at what is the distance, the number of steps that it would take me to get to each of my neighbors within the set of the component that I have. So in this case, this is defined only for components. So I look at all the neighbors that I can reach inside my component, and I measure the distance to each of them. And then my score, my closeness centrality, is going to be inversely proportional to the sum of all those distances. Why? Because it's going to be higher when my typical distances to all my neighbors is small, right? And my distance to my neighbors is going to be small if I'm sort of close to all of them, right? So by taking this ratio, again, we are favoring vertices that tend to be close to many other vertices, and therefore they're central in that sense. Another popular measure of centrality is called betweenness centrality, which is actually counting really literally the number of paths that go through them. So for any pair JK of vertices, J and K, I let GJK to be the number of paths going from J to K. Think about them undirected. So I look at all of the paths that go from J to K, and then I focus of all those paths, how many of them go through I. So now for each pair, I'm going to have this ratio, which is all the paths that go through I divided by all the paths that connect my source and destination. And then I take the sum over all the possible pairs. So vertices that have high betweenness centrality are going to be those that happen to be part of the closest path to a lot of vertices, which means that whenever you're traveling through the graph, chances are if you're taking the shortest path, you're going to go through I. Now, back to some comments about PageRank. You would think that this is a simple idea that came to be in the early 90s. So what Google uses today is by no means anything as simple as what I just said. As a matter of fact, the algorithms that the search engine that Google uses are quite sophisticated and proprietary. They use a lot of contextual information to make their search engine work best. They're highly personalized. So even though the PageRank of a site is something universal, as I said, it doesn't depend on who's searching. It doesn't depend on the person who's doing the search or the keywords that you're entering into the search. You know, that gives you the universal part of it. That's not all that determines how the results are shown to you. In the last step, you can what Google and any web browser does these days is they're going to use the information that you have given to your computer about your own preferences. And those preferences are encoded in a billion different ways, with your browsing history, with the cookies that websites leave behind, with a lot of information that we inadvertently or advertently give to Google and to search engines in general. So what's going to happen is that on top of the universal ranking, our own preferences are going to be superimposed or factored in. A simple way of thinking of the personalization that is still sort of a nice abstract model of what personalization can be is to assume that every time you restart, every time you get stuck and start again, you don't pick with equal probability anywhere in the web, but you pick according to some other probability vector Q. So if every time you get stuck, you prefer to go to a certain set of websites that are the ones that you tend to visit more often, then what this queue does is that it adjusts the ranking based on those preferences, right? So it personalizes to you. So if you do the same keyword search on two different computers, you'll most certainly get a different set of results. And the websites, they're all the same at the bottom, but the order in which they get displayed may look very, very different from one computer to another. Now, just as Google, has kept growing, soon after Google started becoming so important, people started figuring out ways to cheat. As I said at the beginning, it is crucial for a company to be able to appear in the searches at the very top, because most of us don't have the patience to go through more than 2 or 3 result pages. So cheating is a big thing, and understanding what the algorithm does is an important key to figuring out how to cheat Google. I won't go into how to cheat Google today, but there are ways to cheat Google. Of course, every time people figure out how to cheat Google, Google keeps finding ways to find the cheaters. Once somebody gets cheated, they get downgraded so that their website page rank goes down. Another important thing to keep in mind is that the website, the web graph is always changing constantly and continuous time. So the ranks, the page ranks that every website has are constantly being updated, and that's being done in a distributed way with something called web crawlers. They're constantly visited and updating the page ranks as they go along. And the last thing that I want to say is that despite the fact that this is a simple idea, that Google has been around for a while and the internet has grown, the ideas behind the Google's search engine are still pretty much the state of the art, right? It still returns amazingly good results, and PageRank in particular is a very popular algorithm because of how fast and how efficiently it can work. That's it for today. And before we end, I have asked Jose to show you some more simulations to see how in a simulated graph, these different measures of centrality can compare. And you can take a look. Jose?
Yes, hi. So let me share my screen. Oh, is it okay if I think that I need permission.
Let me see. Go ahead.
Let's see. Okay, good. So here I created like a file that shows simulations of the different measurements of centrality that we considered. There's like a version in Spanish and in English. I think I'm going to walk through the version in Spanish. And so so essentially we use the same libraries that we used before for visualizing networks and for generating networks. And we're going to be looking at centrality through degree, from closeness. This is betweenness and PageRank. Okay. And I created a function that essentially calculates all of the centrality measures. And we're going to use data visualization to look at how they behave on different models. Okay. So let's start with the Erdos-Rengi model. Here in this case, I'm generating, as you remember, the Erdos-Rengi model gives like the behavior of the degrees of an Erdős-Rényi is pretty like uniform. There shouldn't be like any vertex that is like extremely more relevant than any other. I'm generating 100 vertices, and on average, I want each vertex to be connected to 3 other vertices. Okay, and the simulations that I'm generated are undirected, so we're not gonna think about directions. Okay, so let's run this piece of code. Generates the graph essentially, and here in this piece of code, I simply generate the networks and I color with darkest colors the vertices that are that have a highest centrality, and I also display them like display the size to represent centrality. So if we look at centrality to degree, we can see that there's like a relatively uniform behavior. We can see that some like vertices like here in the outskirts are clearly not very relevant, and there's like a couple that are like slightly more relevant than others, but it feels like if you only consider degree, like the behavior seems to be kind of uniformly distributed. Then if you look at closeness, which I think is rather interesting, this is closeness. The values are actually even more like tightly close to each other. It doesn't seem to distinguish a lot between them, and it's probably because the graph is not very big, so the differences in like the closeness is not like very high. Then if you look at betweenness, there's like a very clear stark difference. Like the measure of centrality of this like peripheral nodes is like very low, and the relevance of this central node seems to be very high. And finally, with PageRank, we see something a little more balanced, right? So this is for a graph. This is PageRank. So these were the measurements of centrality on a network that is relatively uniformly behaved, right? Like there is no special vertices that are like significantly larger or like more central than others. So let's look at a Chunglu model, which we should remember. Chunglu models are not uniform, so there will be a tendency for some vertices to be way more significant, and we are using Pareto weights. So here I generate the network, and here I simply generate the plots of each measure of centrality, changing the color and the size, right? So let's run that and see what happens. Okay, good. So okay, as you can see here, the graph definitely looks very different, right? Like the original graph, like in the homogeneous case, we didn't see as much of a difference between like nodes, but here we can really see that there is one node that it's quite central when you measure, for instance, through degree, right? Degree centrality. And there's like a couple that are like right behind it. So let's see how closeness behaves. And as we saw before, closeness doesn't really like identify big differences between the different nodes. Then if we look at betweenness centrality, interestingly, it really concentrates a lot of weight on this particular node, which seems to be very central. And finally, if we look at PageRank, we see something again like a little more balanced, and we can see that the most important nodes according to PageRank are this one, and this one, right? And some of the measures like overlap in the sense that they identify important vertices, like common important vertices. Some of them only identify one, some of them don't identify any of them. Like depending on how you measure, you're gonna find something different, right? Is there anything, Mariana, that you wanna comment about these different plots, or should I keep going?
Well, I think you made a comment about the closeness centrality in these examples and the small graph. They're also, it doesn't do such a great job of identifying. I think that black vertex over here, it appears on all of them. So you can see that under any metric, they're all sort of, it's always central to the network under any of the different criteria. One thing I wanted to say in terms of doing this in large graphs, computing the degrees is I guess it's easy to rank vertices according to degree alone, but closeness and betweenness centrality are a little bit tougher to compute. And PageRank, even though it seems that it involves the having the entire adjacency matrix of the graph, in practice it doesn't have to. There's ways of doing local updates that are still guaranteed to find it. So it's quite robust to even the constant changing of the graph, which some of these other centrality measures are not as easy to compute in general. But that's
Okay.
the idea is, the nodes that are going to be central are probably going to be central under many different metrics. And sort of
Yeah.
the intermediate ones that may or may not always be ranked highly.
Good. Yeah, thank you. So to finish real quick, let's go through an intersection model. And remember, the intersection model tends to have like a lot of clusters, a lot of clustering, high clustering, and some of the vertices will have like significantly higher degrees than other. Here we're mixing again with a Pareto. And here, this code here generates the graph, and this code here generates the visualization. Okay, so let's run that. If you have some free time later, you can go and check it out. And let's see. So what do we get? So interesting. So here in degree centrality, we see that there's like a fairly many vertices that have like high degrees and therefore are like important in terms of degree centrality, which would be this one, this 3, 4, 5, 6, and 7, and some others that are like tailing closely behind, right, in terms of degree. And then if we look at closeness, it seems again like, yes, those 7 vertices that were identified by the degree are also kind of like very relevant here, but there is not as much like distinction between them. So again, closeness falls a little behind in terms of detecting relevance. Betweenness, we can see that there is a very stark contrast between the vertices that were like the main vertices and like the rest. We can see that these peripheral nodes almost have like a very low betweenness centrality. And finally, PageRank is here. It's a little more balanced, and it indeed detects really well these 7 relevant vertices. So I mean, this is just a way of illustrating how different measures can tell you different things. I mean, it is possible to generate these visualizations on other graphs, such as, for instance, the Albert Barabasi model of preferential attachment or other models, but these, I think, are quite good at reflecting what we are trying to see. And if you want to check these things out, I think that sometime today, they should be available, both the code and like the document with the visualization. They should be on the webpage of the course. So you're welcome to go and check them out. Thank you.